Right, so this chunk of work looks at how to use standard form. Standard form is generally a higher tier grade C topic, but with problem solving it could become a bit more difficult and have grade B type questions. So what we're going to be aiming to achieve in this, our learning objectives, to represent large and small numbers using standard form, how to turn numbers that are in standard form back into normal decimal form, how to add, subtract, multiply and divide standard form numbers without using a calculator, and then finally we will look at how to use a scientific calculator as well with regard to standard form. Hopefully you will have had a chance to have a look at the Powers of 10 video clip, which is a pretty famous video, but it really powerfully demonstrates what the impact is of increasing 10 by step-by-step increments. So let's get down to the maths. Standard form is an internationally agreed format for writing numbers as a decimal number between 1 and 10, 9.9 recurring, multiplied by a power of 10. And we can write any number using that format. But generally, when we do use it is when we're working with very large numbers or very small numbers, because it just makes it much more efficient than having to write in all the zeros. The best way of going about working with standard form is to remember from primary school your place value grid. So we have a decimal point, and to the left of the decimal point we start off with units, then tens, then hundreds, thousands and 10 of thousands, and each one of those columns is progressively more powerful, has greater value than the previous one. And also to the right of the decimal point we have progressively smaller numbers, tenths, hundredths, thousandths and so on. Now we can write those as indexes, powers of 10, as we saw in the video clip. Now if you can't remember where to start, if you just always hold in your mind that you know 100 is 10 squared, then that one is 10 to the power of 2, and then they would go down to 10 to the power of 0 before we reach the decimal point, and going the other way they would get increasingly larger. So 1000 is the same as 10 to the power of 3. Going in this direction, if you imagine continuing that pattern down, then the first column to the right of the decimal point will be 10 to the negative 1, and then 10 to the negative 2, 10 to the negative 3, and so on infinitely. So if you can just remember when you're working with standard form, all you need to do is just, rather than a fancy grid like this, just jot down a grid starting with 10 to 0 if you can remember, but if you can't, 100 is 10 squared, so it's going 1, 0 from there. The danger is that people will put that one there as 10 to the power of 1. Okay, so the first number we're going to look at is 35,000. So if you write that in, starting with the 0, the first 0, which will be in the unit column, that's what it looks like on a decimal grid. Now what that means is we could write that as 35,000 lots of 10 to the 0. We could write it as 3,500 lots of 10 to the 1. We could write it as 350 lots of 10 to the 2. We could write it as 35 lots of 10 to the 3. Or we could write it as 3.5 lots of 10 to the 4. All of those represent the same number, but the standard form The internationally recognized way of writing it is as a number between 1 and 10, so 3.5 times 10 to the 4. So in standard form, that is going to be 3.5 times 10 to the power of 4. Now I'm just demonstrating there the way that the various ways you could write that as a power of 10, as a multiple of a power of 10. You wouldn't need to do that. All you're going to do is write it in and then read off the tens column that the most significant digit is in. So 3 times 10 to the 4, except it isn't 3 times 10 to the 4, it's a little bit more than that. It's 3.5 times 10 to the 4. So the next number, 4,750, 0, 5, 7, 4. Let's put in our powers. 100 is 10 squared. So we're looking for our most significant. It's 4, so it's going to be 4 times 10 to the 3, except it's not 4 times 10 to the 3, it's more than that, so it's going to be 4.75 times 10 to the 3. And it works for small numbers as well. So with this one, let's put the number in, 0.038 this time. So 100 is 10 squared, 10 to the 1, 10 to the 0, 10 to the negative 1, 10 to the negative 2, 10 to the negative 3. So we could write this in standard form by looking at the most significant figure. The most significant figure, the significance increases in this direction. So the most significant figure is the 3. So it's going to be 3.8, and it's the 10 power that's in the most significant. So it'll be 3.8 times 10 to the power of minus 2. Okay, right, 7 kilometers in millimeters. Well, that's going to be a lot of millimeters, so I just using my sort of knowledge of metric units, I know millimeters is a much smaller measure than that, so this is going to get large, which is why my grid, I've snapshotted my grid going in this direction. So 7 kilometers, I know there are 1,000 meters in a kilometer, so I would times it by 1,000 to turn it into meters. So that's kilometers, that's meters, and I know there are 1,000 millimeters in a meter, so I'm going to times that by 1,000 to turn it into millimeters. So that's going to give me 7 million. So 100 is 10 squared. So 7, 6 zeros. Is going to be 7 times 10 to the 6. So 7 kilometers is 7 times 10 to the power of 6 millimeters. With this one, I'm going for grams to tons. Grams is a small measure, tons is a large measure, so this is going to become progressively smaller. What's going to happen is my 150 grams, I know there are 1,000 grams in a kilogram, so I'm going to divide by 1,000, and I know there are 1,000 kilograms in a ton. Now, what the impact of that does on your grid is, if we were to say we're going to start with 150, if we were to divide that by 10, it basically moves every place value one column to the right. So if you're going to divide by 1,000, it's going to move that, every one of those, 3 columns to the right. So that one is going to end up 1, 2, 3 there. If I write that underneath like that. So dividing by 1,000 on your place value grid moves it 3, each digit 1, 2, 3, 1, 2, 3. Remember, the decimal point isn't a column, it's just in the column, the way that I've set it out. And then when I divide by 1,000 again, well, that's going to move these again 3 columns that way. So that one, 1, 2, 3, would end up there, and the others would end up off the scale, 1, 2, 3. So what we end up with is 1.5 times 10 to the minus 4. Okay, so that's the way that I've done it. I've put in 150, I've divided by 1,000, it moves every digit 3 columns to the right. I've divided by 1,000 again, so that goes another 1, 2, 3, and then I can read off the most significant is in the negative 4 column, so it's going to be 1.5 times 10 to the negative 4. Okay, you can have a go at exercise 1 then. And when you come back, we now look at how we use place value grids to write numbers given in standard form as normal decimal numbers. So it's just a reverse of the process. The 5, it's telling us to put in the 10 to the 4 column. 10 squared is 100. So the 5 goes in there, and then to keep it in that place, we've got to add zeros between that digit and the decimal point. So that will tell us that this is 50,000. Same with small numbers. The 2.34, the 2 is going in the negative 3. 10 to the 0, negative 1, negative 2. So 2 is in the negative 3, 3, 4, and again we need to put those zeros in order to keep the place value positions. We don't need to put a 0 there, but we tend to write the first 0 to the left of the decimal point. So that's going to be 0.00234. When we're adding and subtracting without a calculator, the easiest way to do this is to turn them into normal numbers and then convert them back afterwards. So 2.79 times 10 to the 3. The 2 is going into the 10 to the 3 column. So 2790. And the 4.31 times 10 to the 5. The 4. And then, so these are the numbers that we're going to add together. So if I just flip to a different colour. Junior school edition, 0, 9, 7, 3, 3, 4. So that's the addition, and we want to give this to two significant figures. So the two most significant figures are the ones that are in the columns with the highest place value. So it's going to be the 4 and the 3. We then look to the next column. If that was 5, we'd round that up, but it's not 5 or more, sorry. So it would, to two significant figures, it would be 4, 3, and then the rest are zeros, and that will then mean that this is going to be 4.3 times 10 to the power of 5. And the same when you subtract. So 3.5, put these in first of all, 10 to the 0, negative 1, negative 2, negative 3, negative 4, negative 5. 3.5 times 10 to the negative 1. 2.8 times 10 to the negative 3. So if we load the zeros, and we're subtracting. So we're in primary school non-calculated subtraction. We can't take 8 from 0. So what we have to do is borrow. That becomes a 4. That becomes a 10. That becomes a 9. That becomes a 10. So we end up with 8 from 10 is 2. 2 from 9 is 7. 4, 3, 0. And then to two significant figures, these are the two most significant. The next number is higher than 5, which means it's closer to 0.35, which will then mean it is 3.5 times 10 to the negative 1. When we come to multiplying and dividing, it's the powers of indices that we need to remember. So this is a bit of revision from your indice work. When you multiply a number with the same base, the base is the large number, and the power is the small number that's above it to the right. So when you multiply numbers with the same base, so they both got base 10, you add the powers. So that's going to be 10 to the power of 4 plus 5, 10 to the 9. This one will be 10 to the negative 3 plus 7. So you're at negative 3 in your number line, you're adding 7, you end up at 10 to the 4. When you divide, you subtract the powers. So that one's going to be 10 to the 9 take 5, 10 to the 4. This one would be 10 to the 7 take away negative 3. When you've got two colliding sides that are the same, that means you can replace them with a plus. So that becomes 10 to the 7 plus 3, which is 10 to the 10. And with this one, we're going to have 10 to the negative 2 subtract negative 5. Here's our colliding signs, so that's going to become 2 to the negative 2 plus 5, which is going to take us from negative 2 up 5 places to positive 3. So those are the two laws of indices that we need to use. And what we do is we deal with this, we work with the number parts. So we're going to have 2.4 times 3.1 times, and then we're going to add the powers. This is something that you're going to have to do using whatever non-calculator method you're comfortable with. It seems to me that the most popular at the moment is the Chinese method, so I'll use that. 2, 4, 3, 1. So we're going to have 4 3s are 12, 4 1s are 4, so you write that as 0, 4, 2 3s are 6, 2 1s are 2. You then add up your diagonals starting here, 4, 4, 7, 0. You read off your answer in that direction. So it's 7, 4, 4. You then have to decide where to put the decimal point. However you've been taught, one way is to count the number of numbers after the decimal point in the original. There are 2, so there'll be 2 after the decimal point in the answer. The other way to do it is to think, well, that's 2 times 3, which is 6. So there's no way it's going to be 74.4. It's most likely to be 7.44. So the final answer is 7.44 by multiplying the two numbers together, and then times 10 to the power of 3. Sometimes once you perform the multiplication, this bit isn't in standard form, and you have to then think back how you would change it into standard form. That one's okay. I think the next one is an example of that. So with this one, it's a division. So what we do here is 2.4. If we write it as a fraction, and that's going to be times 10 to the negative 4 minus 7, because we are divided, so we subtract the powers. 2.4 over 3.0 is the same as 24 over 3. If I'm multiplying to get rid of the decimals, both the top and the bottom by 10, as long as you multiply both of them by 10, that's fine. So 2.4 divided by 3, is the same as 24 divided by 30. Multiply the top by 10, multiply the bottom by 10. So if we look to cancel that down, we get 3 goes into that 8 times, and into that 10 times, which is the same as 4 over 5, which is a decimal, is 0.8. So we're going to end up with 0.8 times 10, and here we're at negative 4, and we're going down another 7 places, so we end up at negative 11. But that isn't a number between 1 and 10. To get that to be a number between 1 and 10, I'd have to multiply by 10. So if I multiply that by 10, what I end up with is increasing that by 1. So it's the same as 8 times 10 to the negative 10. There's some for you to have a go at. And then finally, the standard form button on the calculator is that one there, which is my finger's pointing to, times 10 to the power of. So the way that you would type this into your calculator, as I've said there, for H is 8.23 times 10 to the, and then because it's a negative 2, the negative button is that one there. This is an operator, that's a subtract, take away. So negative 2 times 7.6 times 10 to the negative 3 equals. Now you can see 6.2548 times 10 to the power of negative 4. And then you can use your calculators to check the answers to exercise 3. Finally, problem solving. The galaxy that the Earth is in is called the Milky Way. The Milky Way is a disk that is around 120,000 light years across. The Earth is around 27,000 light years from the centre of the disk. A light year is the distance that light can travel in a year, and it is 9.46 times 10 to the 15 meters. Imagine that a spaceship can travel half the speed of light. It sets off from Earth towards the centre of the Milky Way. How long would it take? Okay, so we got to get our head around all the figures that we're given here. It has to travel that far. And it can travel at half that speed. So the first thing to do is to work out how fast the spaceship can travel. So 9.46 times 10 to the 15 divided by 2. Remember the times 10 to the button. So it's going to travel at 4.73 times 10 to the 15 meters in a year. And we have to cover 27,000 light years. So we need to divide the 27,000 light years will be 27,000 lots of that divided by our speed. So we can type that into the calculator exactly as we see it. 27,000 times 9.46 to the 15 divided by 4.73 to the 15, 54,000 years. So it's going to take 54,000 years to get there, travelling at half the speed of light, and our spacecrafts are nowhere near that speed. How many generations of astronauts do you think it would take? Well, a generation is the sort of age gap between you and your parents. On average is between, say, 20-25 years. So if we assume that a generation is 20 years, then we're going to, so the number of generations will be 54,000 divided by 20 . So 2,700 generations. That's a lot of greats. So there we are. That's if you need you to refresh your memory over how those notes are completed. Hopefully that will help you.